Good afternoon, everyone. Today, my topic is rate-dependent bifurcation dodging in a thermoacoustic system driven by color noise. This talk is divided into 4 parts. In the first part, we'll talk about the introduction and the motivation. In the second part, the model of thermoacoustic systems will be introduced. Then, we'll present our results of the rate-dependent bifurcation dodge phenomena. Finally, several conclusions are given in the last part. Firstly, let's give a definition of the tipping. In multi-stable systems, small changes in inputs may cause sudden and disproportionate changes in the outputs. This phenomenon is named as tipping. Some research fields also call the tipping as critical transition or regime shift. To some extent, these changes are irreversible and may cause huge adverse consequences. According to the mechanism of tipping, Ashwin and his co-workers classified it into 3 categories: bifurcation-induced tipping, noise-induced tipping, and rate-induced tipping. B-tipping refers to a tipping phenomenon that occurs when the value of external force or internal parameters slowly exceeds a critical value. For example, the dieback of the Amazon rainforest. Untipping is a phenomenon where the system switches its state after being disturbed by noise. The DO event is the example. R-tipping is a new concept proposed in recent years. For such a case, the parameters of the system are no longer static relative to the variables, but become a new time-dependent variable. When the rate of parameters exceeds a critical value, R-tipping occurs. For example, the global warming. In the current and future climate, the critical factor is the rate of global warming rather than the temperature itself. The conceptual difference between a R-tipping and a B-tipping in systems with a time-varying external input is shown in this figure. For A and B, if external conditions change above some critical rate, the system may fail to check the continuously changing stable state and move away. But for B-tipping, when the critical level is exceeded, it will go to an unstable state. Besides, consider that in nature, the dynamical systems often strongly depend on time, and the parameters will change in a certain time scale. This will affect the states of the systems, so it's highly desirable to consider the rate of parameters in a system. In mathematics, finding R-tipping is an interesting problem because it involves some kind of non-autonomous instability that cannot be described by traditional bifurcation theory or by an asymptotic approach. A typical system considering the rate of parameters is the thermoacoustic system, which is closely related to the burner devices in airplane, rocket, and gas turbine. Tipping in thermoacoustic systems was shown to result from thermoacoustic instability in combustion chambers, and the thermoacoustic instability occurs when there is a positive feedback between the fluctuation of sound pressure and unsteady heat release rate in the combustion chamber. Thermoacoustic instability may lead to a structural damage of rocket and aero engine, compromising rocket launching missions due to engine disintegration. As an important example, in the Apollo program of the United States, more than 2,000 full-scale engine experiments have been conducted on the F-1 engine due to the thermoacoustic instability, consuming a lot of human and material resources. The development cost is about $2.4 billion in 1966, equivalent to $19.25 billion in 2020. Hence, the most important and significant reason to study tipping in thermoacoustic systems is to learn how to dodge the thermoacoustic instability. Considering the nonlinear and non-autonomous dynamical characteristics of the thermoacoustic system, the rate of change of the parameter is likely to be an important factor affecting the thermoacoustic instability. Besides, a series of experiments show that in a system with rate-dependent bifurcation, current noise is more suitable to describe the random force. So our objective is to investigate whether the rate of change of parameters is helped to dodge thermoacoustic instability in thermoacoustic systems excited by current noises. When the development of research, the Helmholtz equation is often used to describe the dynamical behavior of thermoacoustic systems. After Laplace transform, orthogonal basis projection, and truncated Taylor expansion approximation of the nonlinear term, we get this reduced mathematical model of the thermoacoustic systems. By the stochastic arranging method, we can derive the FPK equation. Later, we will use the PDF to describe the random transient dynamical behavior of the thermoacoustic system. The amplitude effective potential function of the model is a double wheel as seen in the time series, the figure 1b. This is consistent with the experimental data, the figure 1a, which shows the rationality of the mathematical model. The time-varying parameter Vt we used is the combination of the cosine function and the linear function. Now let's look at some results. After the introduction of the ramp rate, the amplitude is in fact reduced, and the position of the highest amplitude point is delayed. When the rate is relatively large, the amplitude reduction is stronger, and the phenomenon of bifurcation dodge is more obvious. Next, we studied the influence of the correlation time tau and the intensity d of noise on bifurcation dodge. We found that the larger the noise correlation time tau is, the lower the amplitude becomes, and the better the dodging effect of thermoacoustic instability is. But increasing d would have the opposite effect. Furthermore, we try to find a quantitative relationship between the amplitude and the parameters characterizing the noise. This is the variation of the maximum amplitude AMX with respect to noise correlation time tau and noise intensity D for difference rate R. After simple derivation, we get the Amax and tau, Amax and D have the power law relationship. In addition, we estimate the power law exponents P and Q at difference rates R. For a practical thermoacoustic system, the threshold of thermoacoustic instability is usually defined according to its actual utility. So we present calculations of the probability of a successful bifurcation dodge for a given threshold in the thermoacoustic system. We use the following formula to calculate the probability of bifurcation dodge. We find that the larger R, the larger tau, and the lower D, the higher the probability of successful avoiding thermoacoustic instability. Now there are some conclusions. The avoidance of the undesirable state of a thermoacoustic system excited by color noise is studied. Firstly, we argue that there is a strong reason for assuming that the rate of the parameters affecting the dodging of thermoacoustic instability, and color noise is the most suitable form to describe the random forces in such rate-dependent system. Secondly, the rate of parameter is conductive to dodge the thermoacoustic instability. Besides, we uncovered that the increase of the noise correlation time makes the dodging effect better, but an increase of the noise intensity brings an adverse effect. Thirdly, the functional relationship between the rate of parameters, the correlation time of the noise intensity, and the maximum amplitude of the system are quantified in this work. The power law relationship. Last but not least, the probability of successfully dodging the thermoacoustic instability and the various conditions is calculated to validate the effectiveness of the control. That's all. Thank you.